All right. We're going to do some difficult multiple choice today. So I know this says practice exam on it. Um, I would take that very lightly. These are really good questions for testing the breadth of E&M, but it is not supposed to be taken in the time limit. So if you try this yourself, just sit down and do the questions. Like some of them will take a long time. Like don't think of this as time constraint because you're not going to finish it. But this is a really good overview of kind of everything in the course. So these are just some hard overall E&M questions. Like I didn't try to do 40 hard ones, but I just tried to cover the course content. So there's some of them that I think are easy, but mostly this is just intended to be hard and challenge you. So if you're looking for a more reasonable like difficulty thing, look at the free response section of this. That's a much better like difficulty indicator. So with that, we'll get started. So if this was exam setting, we would expect about 80 minutes on this part. Zero chance I finish close to that. If I finish in an hour and a half, I'm going to call it a good day because there's some crazy items in here. And yes, I know I wrote them, so it's my fault. But the goal here is just to expose you to the content and maybe remember some more like niche aspects of the CED that you might not remember we could test very often. So obviously this is like my own writing and all that. I'm not college born. Like this is way harder than anything you'd get from them. So if you're trying to do this timed and you're getting even close to like if you're getting in the low 30s, that means you have a really good grasp of what's going on out of 40, right? All right, let's do it. Alrighty, two circuits shown below. All batteries and bulbs are identical. What do we want to look at? Bulb brightness. Okay. So we're looking at whether bulb one is brighter or the brightnesses are the same. And we have some justifications. So once again, if you're comparing brightness in circuits, usually the color model of potential is your friend, where we look at our high potential, and then we have our low potential. So we see in circuit one, we drop the entire battery EMF across bulb one, whereas circuit two, well, that's a series. So bulb two is sort of sharing the voltage drop, right? It's actually going to be half and half if these bulbs are identical. So bulb one has a larger voltage drop, red to blue, versus this red to an intermediate color. So the voltage drop is higher across bulb one, so the power is higher. So what justification do we want? Well, the resistance of the circuit is definitely not greater in bulb one's circuit, right? So that must mean there's a greater current through bulb one, which there is, right? Because delta V equals IR. So if there's a larger voltage drop through the bulb, there must be a larger current. I thought this was, as per usual, we try to lead with like an easier one. So again, I'm rating these on my 3-tier scale. 3-point charges are placed at the vertices of the equilateral triangles shown below. These are the same triangle, we're just changing up the point charges. So in our scenario X, this system has total electric potential energy UX, and we want UY in terms of UX. Well, this is about electric potential energy. So we know that electric potential energy is equal to the sum of all the pairs of KQQ over R. And since our R is identical, that means we're really just looking at these pairs, and it can be positive or negative, right? Because if your charges are opposite signs, their product is negative, which means they're sort of bound in energy debt. So how I'd like to do this, again, my goal here with this video is not really to show you the routine way of doing everything, but like some simplifications that make your life a bit easier. So first up, Q and a Q, that's going to be a contribution of +1 to the energy, plus Q and plus Q, that's a contribution of +1, plus Q and plus Q, +1. So the energy of this system is 3. Technically, it's 3kq squared over s, but again, all those distances are the same, so it's not really going to affect our comparison. All right, here we have -2 and 1, which makes -2. Here we have 1 and 1,
which makes positive 1. And here we have negative 2 and 1 again, which gets us negative 2. So if I add this up, I get my green triangle. That total energy there is minus 2 plus 1, which is negative 3. So we see that the energies are equal, but off by a minus sign. There is some computing involved, and anytime the sign of U is involved, I usually say it's a medium. Right. A ion with charge is traveling to the right before entering a magnetic field. We want the radius. So this is a very standard problem, finding the radius in a magnetic field. So anytime you see circle, we know that mv squared over r is involved. That's sort of our centripetal force. So we know that that is absolutely involved. And what is causing the mv squared over r? Well, what's causing us to move in a circle? It's the magnetic force, QVB. So we can cancel out a v, and we get mv over r is equal to QB. Then we can simplify more, and we're solving for r, so we get mv equals QBR. So r would be equal to mv over QB. And we can plug in our values just to see what that's going to be. So this is a calculate question because I wanted us to have to derive this result instead of just remembering it from symbols. So we got 2 times 10 to the minus 8. V was 5. Q was 40 microcoulombs, so 40 times 10 to the minus 6. And B was 0.02. So let's see here. Based on the powers here, we are going to get answer choice C, 0.125 meters. Because I can tell, because the 2's are going to cancel, and I have 5/4 essentially. So it's 1.25. Just because you had to derive some things here, like you actually had to come up with the expression yourself. It wasn't necessarily plug and chug unless if you knew the formula. So medium. Electric potential along the axis is given by this function. What's the maximum force? Well, if you have a function, you know you're doing calculus. And if I want electric force, that's going to relate to field. So I do have this relationship that says the electric field is minus dv dx. So I can just take an x derivative of a times sine of bx. So I have to remember to do the chain rule, and I get negative ab cosine of bx. But this actually isn't what we want. We want the force on a test charge. So force is equal to QE. So I just attach a Q in front of that. And it does want the sort of maximum force. So we can just take the amplitude, right? Because this is bounded. So we can just take ABQ, or I guess QAB. So it's medium once again. People always forget that this relationship exists. People forget you can just differentiate, right? Because E is the slope of the terrain. All right, 3 spheres are placed along the x-axis. Which sphere, if any, experiences the greatest force due to the other spheres? So please do not compute this, right? There's a lot of symmetry here, so let's just draw some arrows. So I'm going to color code my spheres. All right, so my sphere X. Well, sphere X is going to be attracted to Y, and that's going to be a strong force because that's a small distance. And it's also going to be attracted to Z, but that's a smaller attraction because Z is farther away. Then sphere Y is going to be attracted to X, and that's a strong force because that distance is small. And it's also going to be repelled from Z, minus minus, but the Z is also just as close, so we get a big repel there. And then for Z, Z is going to get repelled strongly from Y, because that Y is close. And it is going to get attracted to X, but X is far, so that's a weaker attraction. So we can actually see here that if we were to do our rankings, Z would be the lowest force because there's cancellation. Then it would be X because there's addition, but one of the spheres is farther away. And then it would be Y that has the maximum force exerted on it because it's additive forces, but also the spheres are closer together. All right, let's consider the following arrangement of point charges. We have a plus Q and a minus Q placed on the y-axis, and we want the electric field along the x-axis, positive x-axis at least. Now, you can do this without actually deriving an expression because you'll see that the only difference is if there's an x or a y, and obviously what direction the field is in. So we can kind of figure that out already. So you can totally derive this, by the way. So plus Q is a source, so it's going to push there. And minus Q is a sink, so that's going to pull here. Not my best job at symmetry. So we can see that our net E field is just going to be down. So be careful. It's not just along the x-axis because this is a minus Q, so we have to think of that as a sink. So be careful. We spice it up sometimes. So we know it's C or D, and then we have to decide what goes on the numerator. So we know here that like our E net is going to be 2 times the y component from one of the charges. So it's going to be 2 times kq over r squared times a trig function. And we always define using our usual sort of polar angle for these. It's just usually more convenient. So we take our angle here just to be theta. So we multiply by sine theta. So we'd get 2 times kq over r squared, which is x squared plus y squared, times sine theta, which is opposite over hypotenuse. And that will be answer choice D. Even though this can be done easily, I'm giving it hard. I'm giving it a ranking of hard. So again, the like traditional way of doing this would be like label your sides of this triangle and do the trig extraction, but this is not a FRQ. We have the answer choices. So also you can plug in. So if I plug in x equals 0, this term goes away and this one doesn't. So the field actually shouldn't be 0 at the origin because I'm getting pushed away and sucked in from each charge, so the fields add, not cancel. So I should not get 0 field, which tells you that x cannot be in the numerator. All right, calculate the energy stored by the 3 microfarad capacitor in the network shown below. Well, anytime you have a network of resistors, capacitors, etc., you got to find the equivalent quantity, find the total current or charge, and then start working out breaking the network back down. So we first want to find CEQ. So our equivalent capacitance, well, capacitance does the reciprocal in series, and it just adds normally in parallel. So 1 and 3 makes 4. So my equivalent capacitance would be 1 over 4 plus 1 over 4 to the negative 1, because I essentially just have 2 4 microfarads in series. And anytime you have identical capacitors or anything that's adding via the reciprocal rule, it turns into division. So I have 2 copies of 4, which ends up being a 4 divided by 2. And why that helps is because now we can use the fact that the total charge on the network, using the fact that C equals Q over delta V, this is a definition, we can find that the total Q is equal to the equivalent capacitance times the battery EMF. So we just do 2 times 8, which would be 16 microcoulombs. So that tells us how much charge we have access to on this network. Now, there's a real shortcut solution that you might have noticed, but we'll go over that later. I'm showing the traditional way first, and then we'll show like the galaxy brain way of doing it. But We can then find the delta V across the first capacitor, because the first capacitor is in series, so the charge hasn't sort of junction ruled out yet. Because we know that all the charge is going to go to the first capacitor, and then the charge is going to split up, with the larger capacitance requiring more charge to get that potential difference. But the delta V across the first capacitor is just Q over C, where this time it's actually the total Q and 4 microfarads, so we get 4 volts. Then we go over here. We know that our delta V across the 3 microfarad must also be 4 volts because of loop rule. So we just said that this voltage drop was 4 volts, so this voltage drop must also be 4 volts. And then we can just use a capacitor energy formula. You could solve for Q at this point, but I think it is just super important that we know all 3 variations of the capacitor energy formula, so we can just plug in. So we get 1/2 times the 3 microfarad times 4 squared. So that would be 8 times 3, which is 24 microjoules. Now that took us a lot of time. So I did actually write this problem that if you made a certain observation, we could get this done a lot quicker. So if you noticed, you could have actually done this by just seeing that 4 and 4 are identical capacitors. So they must just share the voltage drop equally, and you can just do 1/2 CV squared from there. Now, if you wanted to do 1/2 Q delta V, once you knew the voltage drop was 4, you could just do Q equals CV. 4 times 3 is 12 microcoulombs. So then you just do 1/2 Q delta V. So 1/2 times 12 times 3. 1/2 times 12 times 3, does that work? Yeah. Sorry, 1/2 times 12 times 4. Okay, oh boy, multi-battery circuit. So I'll show a couple ways of doing the multi-battery circuit. Determine the current through the resistance R. So first I'll show you the loop rule way. So the problem with this is that there's all these currents going on, where there's a current that we want through this resistor. There's some current we don't want through this resistor, and then there's some junction rule thing that's happening here. So we could write like a series of loop rules, but again, the goal is to avoid this resistor because we don't know anything about it. So if we just draw a giant loop around the circuit like this, we can create a loop rule equation. So we know that the sum of all our delta V's has to be 0. So if I start from here, I travel through a battery uphill, so it'd be plus the battery EMF. Then I drop IR through the resistor because I'm going with the current, so it's a drop. Then I go across the battery, the other battery, except I'm still going from negative to positive, so it's still a gain. And then after all that, I have returned. So that is my loop. So we just get 2 copies of the battery EMF is equal to IR. So I is just 2 times the battery EMF over the resistance. Now, there's another way of doing this that is kind of doing the loop rule, but it uses color coding as well. So if you got to pick somewhere to be 0 potential, which is fine. So let's say I pick the bottom of my circuit to be 0 potential. That's totally fine. You can pick 0 potential wherever you want. So this would be 0 potential. So what that tells me is that here, my potential gets stepped up by a factor of script E. But then over here, my potential would actually get stepped down by a factor of script E. So actually over here, my potential would be 0, and then script E lower. So this is actually minus E. So then you could see by Ohm's law that since this potential difference would be the difference between 1 script e and negative 1 script e, which would be 2 script e, you could then just do I equals delta v over r and get it that way. But this is the intended solution, is this loop rule. All right, now a quick break from that. Consider the three circuits shown below. Each resistance is identical. All inductances are identical. Rank the steady state current. So steady state current, and this is an inductor circuit. So the inductor becomes just a wire at long times. The inductor is not unhappy anymore. So we can pretend the inductor just doesn't exist in any of these circuits when we're looking at steady state. So if the inductor doesn't exist, and we're looking at the currents, well, of course, we're just looking at Req. So here we just have an R, so this resistance is R. Here we have an R and an R in parallel, so that turns into division, so this would be R over 2. Then we have two R's in series, which is just 2R. So we see that the lowest resistance would have the most current, that's circuit 2. Then we have our middle resistance, then we have the most resistance. So 3 is last, and 2 is first. I think I ranked this level 2. Oh yeah, and in case we didn't realize, anything with multiple batteries is probably getting 3-star. And this one, it was computation heavy, but the skill set wasn't crazy, so I actually still left that as 2. All right, now we got another reasonable one. In the diagram below, we got point charges around this sort of square. If the magnitude of the E field due to one of these point charges is E, what is the net field strength? Well, we know that the positive sphere is going to be a source that pushes away, generates a field E. Negative Q, that's a sink, so that would be attractive. That would be E there. So we're just figuring out what this sums to. Well, these don't cancel, so the answer is definitely not 0. They definitely interact some way, so the answer is not just 1. And they don't add completely, right? They don't just add 1 plus 1 equals 2. They're not in the same direction. So we know the answer has to be root 2. But again, this is just Pythagorean theorem, right? We have 1 squared plus 1 squared under a square root, which is square root 2. I thought this was an easy one. So you could tell, I think, that it was Pythagorean. All right, square conducting loop is placed near a wire. We want the magnitude and direction of the net force on the loop by the wire. So there's a couple ways that we could do this. First, we got to get our forces. So we know that our current directions is going to be as follows. Then we know that from our either right-hand rule or just wire attraction rules, the B field would be into the page. So we get like a large B field into the page and then a small B field at the other vertex. We could do our QV cross B to see that this side gets repelled and this side gets attracted. Or you could just remember that opposite currents repel, like currents attract. So we know the net force is going to be repulsive. Then, to actually figure out the magnitude, we can use our formula for the force between two wires. So we know that F between two wires, which is not on the formula sheet, but is absolutely worth memorizing, is mu naught I1, I2 divided by 2 pi r times L. So we'll just do that for each of these. So for the left side, we have mu naught. Both currents are I. The length of the square is L times 2 pi. And the distance away from the wire is 2L. Then we subtract the force from the other side, which is mu naught I squared L over 2 pi times not 2L anymore, but now I'm 2L plus L away, right? I've crossed the square, so it's 2L plus L, which is 3L. We see some L's cancel, so we end up getting 1/4 mu naught I squared over pi minus 1/6 mu naught I squared over pi. which is equal to 1/12 mu naught I squared over pi. And we said the repulsive force was going to win. 3-star. Now, if you knew there was a sort of attraction repulsion thing, you could guess that the distractor is you adding the forces. So this is what you get by addition. So you could have eliminated these really quick. The goal here is like, yes, I know I'm taking a ton of time going through this. This is a multiple choice test. As soon as you figure out what the answer has to be, you can circle it and move on. So realize that usually with these 2x2 tables, one of the answers is going to be subtraction based, the other is going to be addition based. So if you figure out what's going on there, you can get your answer. All right, conductors. A conducting shell holds positive charge. Point P lies within the cavity. Assuming potential is 0, very far away, which is true about the electric potential at point P? So this is an example of conductive shielding, where we are inside a metal. This is like your car in the lightning strike. So we know a couple of things. We know that inside a cavity, or any shell, E is 0. And we also know that V is constant, but not usually 0. So we're not asking about E, we're asking about V. And unless we're very far away, V is probably not 0 inside this conductor. So our claim is that the potential is non-zero inside this cavity because the electric potential remains constant. Because we know there's no electric field in the cavity, so it can't be the other justification. And also, this justification is not true. And this is true. There is no electric field within the cavity, but that says E is 0, which means V is constant. Level 2. That's a tricky one. All right, we launch a charged particle towards these two B fields. We want to compare the net magnetic force on each particle in the field. Magnitudes, of course. Alrighty. So, again, what is the magnetic force? Well, the magnetic force on a particle, the magnitude of that would be QV perpendicular B. And notice in both of these cases, the right-hand rule works. Because in case 1, I could do QV cross B, that's into the screen. And the other one, I could do QV cross B, that's up. So I get a force in each of these cases. V is entirely perpendicular to B in both of them. So the forces are equal and they are not 0. This is just right-hand rule. Now, if one of these fields pointed to the left or right, then you'd get 0 force because you'd get 0 perpendicular component. So both of the forces in this case are QVB. They're just in different directions. All right, a negatively charged particle is moving to the right. Which of the following gives the direction of the conventional current generated by the particle, as well as the direction of the net magnetic field at point P? So we have to think about what a negative charge is, right? A negative charge moving to the left. Well, we want conventional current. Conventional current is the direction of positive charge flow. So electrons go opposite the direction of conventional current. So what this actually tells me is that really what I have here is if I want to pretend that my electron is sort of a little wire, it's going to actually carry a current to the left. Because if negatives move to the right, that would mean that positives would move to the left. And then if you do your right-hand rule, I see that my fingers pop out of the page at that point. And another shortcut is if you're looking for the field from an electron, you can just use your left hand. You can just do the wrapping rule there, and it still pops out of the page. So left and out of the page. I did actually think this was 1 star, because it's just right-hand rule. Oh, lovely. All right, we have a charged sphere of mass m and charge plus q. It's placed at this very suspicious distance along the axis of a charged ring. Radius r, we release the sphere from rest, and we want its kinetic energy upon passing through the center. Alrighty, lovely. Well, we're looking at kinetic energy. So this is really the only equation we have is delta K is negative delta U, which is negative Q delta V. So we just need to find the potential difference between these 2 points. So we don't actually need to use calculus to find the potential for these, because if you notice, sort of every point is going to be the same distance away from Q. So we can just use the good old point charge formula. Potential is KQ over R. And technically it's negative KQ over R in this case because it's a minus charge. So that would be our potential sort of at the center. So V at the center is negative KQ over R because all of my Q is just surrounding me a distance R away. Now over here though, at the sort of starting point or this release point, well, we can see we can make a right triangle out of this with legs r and square root 8 times r. So that means this Pythagorean distance would be the square root of 1 squared plus 8 squared. No, of 1 squared plus square root of 8 squared times r, which is equal to 3r. So our potential at the starting point along the axis is negative kq over 3r. So we had to do that Pythagorean theorem 1. And then we just do our delta v. So our delta k would be negative delta u. So negative q times our delta v. Well, our delta v is going to be our final potential, negative kq over r, minus our starting potential, which was negative kq over 3r. So we get 1 minus a third, or negative 1 plus a third, so negative 2/3. So we get negative q times negative 2/3 kq over r. So our change in kinetic energy, which will be our final kinetic energy, is 2/3 kqq over r. Yeah, that's absolutely hard, right? Very tricky. All right, the circuit shown below, the battery has a resistance of 2 ohms. So anytime your battery has resistance, that means you just got to add a resistor in. We want the current through the 12 ohm resistor. Well, again, what we know here is we can just sort of do Kirchhoff's rules, right? If I can actually color my potential correctly. This is going to be similar to the capacitor type problem. Where we're just going to REQ this. So REQ is going to be the 2 is in series with this parallel combination of 12 and 6. And 12 and 6 in parallel, if you compute that, that is going to be 4. So you actually get 2 plus 4, which is equal to 6 ohms. So this means my total current is just going to be the battery EMF divided by REQ, which is 18 over 6, which is 3 amps. So that's not the answer, right? This is the battery current. So this is the total current that's coming into the battery. So now we just got to do some more of Kirchhoff's rules. So now that we got the battery current, we want the current through the 12 ohm. So we know there's going to be some sort of a junction rule splitting that happens. So to figure out how that splits, we know that by Ohm's law, delta V equals IR. So all 3 amps are going to hit the 2 ohm resistor from the battery. So actually we drop 6 volts inside the battery itself. And then based on the loop rule, that must mean I drop 12 volts across the 12 ohm to get our sum to be 18. So doing that, that gets us, well, just I through the 12 ohm is just going to be its delta V divided by R. So we drop 12 volts. And the resistance is 12, so we get 1 amp. And you could have actually reasoned this has to be the answer, because we know that sort of at this junction splitting point, we're going to get some current that goes through the 12, some current that goes through the 6, and the 12 is twice the resistance of the 6, so we only need half the current. So we know the current is going to actually split into thirds like this. So again, just try to think of those time-saving tips that prevent you from having to do the whole process. Now, this is just a pretty standard combination circuit, so that gets 2 star. All right, now we got some RC. Determine the charge stored on the positive plate of the capacitor after a long time. Well, after a long time, that means that the capacitor is equal to a gap. So this means our effective circuit is just a hole. There's just a hole right here. So if we were to try the potential color code, we see that with the long time capacitor, we don't get, this is closed, we don't get sort of a short circuit. We get always what I've been calling sort of the long circuits, because the current has to go all the way around. We can't be shorted. So REQ here is just going to be the battery EMF divided by 1, 2, 3, 4 R's. Or sorry, this is I. And then notice that to find the charge stored on the positive plate of the capacitor, we need to use Q equals C delta V. And I should have actually said the capacitance is C. That's an error on my part. The capacitance on this should be C. We need to find its delta V. So notice that my potential difference across my capacitor is orange to blue. That's the same potential difference as the 2 and the 1 the 2 and the 1 2 and 1 R in series together. So delta V across the capacitor is the same thing as the delta V across 2R plus the delta V across the R, which is just equal to the current times 3R, which is their equivalent resistance together. So we get 3/4 of the battery EMF. There's other ways of doing this. So another way of doing this, which is probably easier, is once you find your total current, you can see that you drop a quarter of the EMF across the first resistance, which means by the loop rule, you must drop 3/4 across the other, any other part of the loop. I ranked this 3 stars. That was a tricky one. All right, I got 2 cylinders connected to a battery. Both cylinders of equal length and are the same material, but Y has a larger radius. Which of the following compares the delta V across each cylinder? So anytime you see like physical resistors, you know it relates to R equals rho L over A. And the area of Y is larger than the area of X. So RY is larger than RX. Or sorry, other way around. RX is larger than RY. Because this is like breathing through a small straw. This is like breathing through a long straw. You get more airflow. So you get a larger resistance in X because it's narrower. So we're comparing the voltage drop across each resistor now. And this is a series. So delta V is just equal to IR. And we know that in series, I is the same for the 2 circuit elements. So if X has a larger resistance, it must also experience a larger voltage drop. And we see that would be A. Because this is just testing series and parallel. Like this is obviously not true. The parallel one. I thought this was level 1.
You'd have to think that you just have to reason the bigger resistance must have more of your voltage share. All right, a cart of side length S and resistance R moves through this B field. Which of the following differential equations could be solved to determine the speed of the cart while entering the field? So we know that while entering the field, there's going to be a Lenz's law drag force that fights the cart's motion. So we know here we're going to use the fact that F net is equal to the helping forces minus the hurting forces, but there's no forces helping our cart enter, but the bill force is fighting our motion. And what is, well, we know I and we know L, or sorry, we know L, or L at least, it's the side length of the square. And then what is the current? Well, this is motional EMF, right? We're moving into a B field. So we can use the relationship that motional EMF is VBL, or VBS in this case. So the induced current is just going to be Ohm's law, delta V over R. So we can just replace that I with VBS over R. So we get negative B squared S squared over R times V. And that's just the net force. So this is F net. So then acceleration is just going to be negative. It's just going to be F net over M. So we just tack on an M to the denominator. And acceleration is dv dt. So just be careful that you don't stop with net force. So that would be D. Or if you've done this so many times and you just know this is the answer, you can pick that one. This is a standard diff-EQ that I expect we've seen a lot at this point. All right. An infinite line of charge, we give it a charge density. We want to calculate the net electric field above this line. So it's an infinite line of charge. This is one of our Gauss's law base cases. So a lot of people tried to do this using our E field definition, and you'd have like an infinite integral to evaluate. So that's probably not a good choice. Now, you have Desmos, so you could actually numerically estimate it, but I don't know if that's worth your time. This is like a two-line Gauss's law. So the fact that this is an infinite line of charge means that the field will just point radially out at all points. So the field is just going to pierce this cylinder. That's why we draw the cylinder, because that marries nicely with this field. And then we're going to be enclosing some charge inside this cylinder. Now, the radius of the cylinder, that's real. That's the sort of length we want to find the field at. But this length x is sort of completely arbitrary. So we can use Gauss's law, which says integral of EdA equals the enclosed charge divided by epsilon naught. We chose to use a cylinder, which has area 2 pi r extended a distance x. And the enclosed charge would be lambda, which is charge per unit length, times length, divided by epsilon naught. So the x that we made up goes away. So we get the electric field is just going to be lambda over 2 pi epsilon naught times 1 over r. So we can just sort of evaluate these things now. So lambda was 5.56 times 10 to the minus 9. And epsilon naught is 8.85 times 10 to the minus 12. And r is 0.2. So plugging that in, notice that, let's see, what are we going to get here? Can I reason through what the answer should be? No, I got to calculate it real quick. My guess would be it's 500. So we have to take a brief intermission while I punch this into Desmos. 5.56 divided by 2 pi times 8.85. Yeah, it's 500. So do not forget that this is just a Gauss's law thing. If your line of charge is very long, you can just use Gauss's law. You don't have to integrate or anything. Alrighty. Consider the arrangement of charged spheres below. All tick marks are equally spaced. If the electric potential at S is Vs, what's the electric potential at T? Assume V equals 0 at infinity. Okay. Well, electric potential, this is not arrows, right? Electric potential is height. So we just need to find sort of the height contributions at each of these points. So I am going to color my spheres like I normally do. Let's use the same coloring as before. So my blue sphere, that's going to generate a potential of like +1 unit at S and +1/3 unit at T. Right, so it's linear. So I'm 1, 2, 3 units away. So it's a third of the potential. Then my green sphere is going to generate 1 unit of positive potential there, 1 unit of positive potential there. And then my purple sphere, this is actually negative. So I get 1 unit of negative potential at T, and then I get 1, 2, 3, so negative 1/3 units there. So this says that Vs would be equal to, let's see, 1 plus 1 is 2, 2 minus 1/3. I'm totally blanking on what 2 minus 1/3 is. 5/3, wow. And then the potential at T, okay, that one I can do. The potential at T is just 1/3. So we see that Vt is this number divided by 5, right? I thought this was level 2. This was just kind of gross. I don't really like this problem. The numbers didn't work very nice. I wrote it like it's my fault, but thought you were done with Gauss, huh? All right, an insulating sphere, radius A, holds charge Q, uniformly distributed. What's the net electric field from the center of the sphere inside the sphere? Can't use units because all the units work out. So we got to figure out the power. Now, if you know this fact, if you know E field is linear inside a uniform insulator, you can instantly say it's C. Let's prove that. So this is a graph that I suggest you just know that E for an insulator of uniform charge density looks like this result, where the maximum is at KQ over the actual radius squared. This is on the memorized list, but let's actually show that we get this result inside. Now, there's a couple ways of reasoning through why it's linear. Like there's one that says like E field is KQ over R squared. And the enclosed charge, that's based on volume, so that grows cubically with R. So we know we're dividing a cubic by a quadratic, so we're left over with an extra R in the numerator. But of course, the intention is to use Gauss's law here. So integral of EdA equals Q enclosed divided by epsilon naught. We're using a Gaussian sphere. So we just got to figure out what is the enclosed charge. Well, the enclosed charge is just going to be the charge density times the volume. And my charge density would be my total charge Q divided by my total volume times my enclosed volume, which would be the volume of the smaller sphere. So we get E times 4 pi r squared equals 1 over epsilon naught times Q times this interesting quantity that we've used before that we call like the volume fraction, right? It makes sense that the enclosed charge is like the total charge times whatever proportion of the volume you're enclosing because it's uniform to the volume. So we see that E is 1 over 4 pi epsilon naught, which is, of course, K. times Q over A cubed times R. That's how you get that result. Now, this was not really the intention. I was hoping that we think about linearity. Like I made all of the functional dependencies different so that you actually had to work this out. So that you didn't actually have to work it out. So if you knew the field should be linear, that actually gets you C. I did that purposefully. All right, 3 long wires carrying current perpendicular to the plane of the page are shown below. We give you the value of D, calculate the force per unit length. So this also uses our fact that force per unit length for wires is mu naught I1 I2 over 2 pi r. Because that's just the force formula with a length divided out. So once again, we want this force sort of on the 2 amp current. So opposite currents actually repel. So I'm going to have a leftward repulsive force from the close current. And then I'm going to have a rightward attractive force from the like current. And I know that the left is going to win because this current is 1.5 times as strong, but it's twice as far away. So the weaker field actually beats it out there. That effect wins. So we just go ahead and compute. So our net field here would be mu naught over 2 pi times we'll just plug in the values. Mu naught is 4 pi times 10 to the minus 7th. Then the product of our first two currents would be 0.2 and 0.4. And those are separated by 1d, which is 0.1 meters. And then we subtract off the 0.2 times the 0.6, which is separated by 2d's, so it's 0.2. And this works out really cleanly. We see that we get a 2 times 10 to the negative 7th on the outside, and then we get 0.8 minus 0.6, which is 0.2. So we end up getting 4 times 10 to the negative 8 newtons per meter. And that's going to be answer choice A. I still said this was a 2-star. It's plug and chug. Also, this is a piece of advice I forgot to say. If you see numbers, probably skip it. Skip the numbers questions. Like, this is so time consuming, typing in this garbage into the calculator. So that's just not worth your time. Yeah, not worth it. Okay. So the cube shown below, we're going to find the flux sign and the enclosed charge. Well, anytime you see flux and enclosed charge, we have to use Gauss's law again, except this time we use the fact that Gauss's law says that electric flux is Q enclosed over epsilon naught, or namely that flux only depends on Q enclosed. So, well, I see that my cube has more field lines that exit than enter. So that must mean there's some sort of a source spawning field lines inside this cube. So there's a positive charge because the flux is positive. Right, because we said that flux, we say that outward flux is positive. Because positive charges generate positive flux. We want that sign convention to be true. Determine the time constant of the circuit below. Well, we know what time constant is. This is RC. So the time constant of the circuit is RC, as long as we do the equivalent RC of the circuits. So we just got to break everybody down here. So I might do like a couple redraws now. We'll do it live. Okay, so these capacitors are in series. So this is the only thing I have to do to the capacitors. So capacitors are in series, so I just do the reciprocal rule. 1 over 1 plus 1 over 1 to the negative 1 is 2 to the negative 1, which is 1 half. So this is C over 2. Then these resistors make 6 in this bottom branch. This makes 2, and this adds on 1 to that. So our equivalent circuit is going to end up looking like this. This is going to be like our first redraw. So the top branch of resistors, 4 plus 4 is 2 in parallel, plus another 1 is 3, and then 4 plus 2 is 6. And then we said down here that our equivalent capacitance was just going to be C over 2. And we've done this resistor a million times, that 3 plus 6 in parallel is 2. So we just get a 2R and a C over 2. So tau is just going to be REQ, which was 2R, times CEQ, which was C over 2. So we just get RC. I ranked that level 2. There's enough combining rules that you had to do that. Could I have done this with less resistors? Probably. Yeah, I don't know. Again, this is not really reflective of the time constraint. Like if you're doing this yourself, just try to do the problems. Don't worry about the time. I didn't really think about this as the timed test. I thought about this as just good content. All right, hollow cavity surrounded by 2 conducting shells. The inner shell has radius. They basically go R, 2R, 3R, 4R. And both the shells have net charge plus Q. So this is going to be about like how the plus Q likes to distribute itself using the surface charge theorem. So we want the net potential at the center of the cavity, assuming V is 0 far away. Okay, well, surface charge theorem says the inner surface cancels whatever charge it is staring at. So this inner surface is staring at nothing. There's no charge in the cavity. So I have 0 charge here. Then for the outer surface, it holds whatever's left. Or alternatively, it holds sort of the net charge of everything inside the circle you draw. So that must mean all of the plus Q goes to the outer surface. Now we do our next set. So for our next set of charges, our inner surface is now staring at a plus Q. So our inner surface of the outer shell stares at a plus Q. So we have to cancel that with a minus Q. But then in order to get the accounting to work, we still have to somehow add up the outer shell to plus Q. So that would mean that there must be 2 Qs on the outside. And another way of seeing that is that outside the system, if I draw a giant circle, I have a shell with Q and another shell with Q, so there must be 2 Q out there. So now we can just find the potential, because the potential is the sum of KQ over R. So if I do this with all the surfaces, I have a charge Q, a distance 2R away. I have a charge of minus Q, a distance 3R away. And I have a charge 2Q, a distance 4R away. So we can sum those up. So we'd get 1/2 KQ over R minus 1/3 KQ over R plus 1/2 KQ over R. So we'd get 1 minus 1/3, so we'd get 2/3 KQ over R. There's an absurd way you could do this using like integrals, but that's not worth it. I thought this was still advanced because you had to figure out all these charges and connect it to KQ over R. All right, square conducting loop is entering a B field, inducing a current I. What happens if we construct a side length, a square of twice the side length using wire of the same resistivity and cross-sectional area? If you ever see this word, resistivity, we have to be thinking that the geometry matters. So this actually does tell us that like we need to use this fact somewhere. What is the new induced current? Okay. So we have, once again, this is motional EMF. So motional EMF is VBO. But we don't want motional EMF. We want this sort of current induced. So my induced current is VBO over R. So we just got to do our multipliers. Speed is the same. B field is the same. Length, well, I'm doubling the side length of the square in the B field, so my motional EMF doubles. But also, we're actually saying the resistance sort of matters here. So I'm also constructing a loop that has twice the length of the original one. And it's the same cross-sectional area and resistivity. So I'm actually also doubling the resistance. So those two effects actually exactly cancel. This is arguably level 3. Like this gets level 3 not because it's actually hard, but because this is like a trick. Like I'm not a fan of this question. I mean, I know I wrote it, but that's because I've seen it before. And it's something you should be aware of, that sometimes you have to take into account the geometry of these loops that are changing. All right, in the circuit shown below, the switch is initially open. The switch is then closed. Calculate the rate of change of current in the circuit when the voltage drop across the resistor is 4 volts. Okay, rate of change of current in a circuit. That is not really something we have formulas for, except this is a L over R circuit, so we know that there's an inductor formula. We know that delta V across an inductor is equal to L di dt. So all we have to do is figure out, and we know what, so this tells us di dt is just delta V across the inductor divided by its inductance, which we know is 0.05. Well, it says the voltage drop across the resistor is 4 volts. So anytime you know things about a circuit and voltage drops, we should probably be thinking of loop rule, right? Because if we do this, our loop equation would be like the battery EMF minus delta V across the inductor minus delta V across the resistor equals 0. So 12 volts minus delta V across the inductor minus, we're given the voltage drop is 4 volts across the resistor. So delta V across the inductor is going to be 8 volts. And we can actually just see this really easy if we just draw in our voltage drop here, right? If that voltage drop was 4, this voltage drop has to be 8. So we can just plug in 8 divided by 0.05, and that is 160. Amps per second, which is a huge number of amps per second. Like that looks crazy. We're never going to have 160 amps in these circuits. But again, remember the time constant is so small that this reaches steady state almost instantaneously. If you calculate the time constant of this circuit, it's so small. So yeah, this is like a huge number, but that's because the time scale is so quick. It's a huge rate of change, but for very small. This was loop rule. There was a couple steps. That gets 2 star. Parallel plate capacitor is charged and isolated. The plate separation is then increased. Which of the following statements and justifications are true about the energy stored in the capacitor? Does it increase or decrease? Well, our capacitor is charged and isolated. Isolated is very important. There's 2 capacitor cases, isolated and connected to battery. So this is isolated, which means our charge, our charge is constant. So we cannot lose charge. So now we have to think about what happens to the energy stored by the capacitor. So the fact that Q is constant means that we probably want the energy formula involving mainly Q for the capacitor. So our Q stays the same. Our Q stays the same because our capacitor is isolated, but also we're increasing plate separation. So we know that capacitance is kappa epsilon naught A over D for parallel plates only. but these are parallel plates. And we are increasing the plate separation, so capacitance must decrease. So we are keeping the charge constant, but we're decreasing capacitance. So this means we're dividing by a smaller number, so the energy stored increases. So why does the energy stored increase? Well, we know the charge on the plate doesn't increase because charge remains constant. So why does it increase? Well, it costs me work to separate, right? These plates are pushing against each other. So I must have had to put some energy in to separate them. So that's that. I actually thought the explanation gave this one away. So I called this actually 1 star because I thought the explanation gave it away. Because you could, if you thought the energy was going to increase, you could totally get rid of this one. And also, this is just, yeah, it's you could as soon as you see the energy has to increase, this is just kind of a known interpretation of why energy increases when you separate an isolated capacitor, right? Because it has to cost you work to fight the electrostatic attraction. All right. Infinite conducting slab. Oh, how lovely. Infinite conducting slab. The slab is centered at z equals 0 and carries a current density that varies. Which of the following could be the magnetic field strength as a function of C? So we have linear constant, we have concave up constant, we have linear, then the decay, and then we have concave up and the decay. So one thing we need to remember is that we know it's going to be A or B. Because whenever you keep adding dimensions to these objects, we get less and less of an effect or a fall off in the denominator. Now, we can definitely just prove this with Ampere's law if we would like, but that's not the intention of the problem. Like, I really think it's important we know the fact that if you have planes or slabs, the E field or B field generated is going to be constant outside. So we know it's going to be A or B. And then we have to think about what's going to happen here. Well, we have a density function. So we just said that if you have a uniform density, uniform density means your magnetic field or electric field would increase at a uniform rate. So a density function would mean that our field increases faster because we're packing more current. We're packing more current at farther distances from the center, so it has to be B. I did think this was 3 star, figuring this out. If you did this by hand, really cool, I guess. Like, I don't really think that's a skill that's going to be super important if you do it, but you will see the quadratic dependence. So I think I just want to explain this better, why I know this is the answer. So first of all, every time you add a dimension to your sort of distribution, you remove an effect from the denominator. So we said a wire, which is 1D, falls off like 1 over r outside. So if I add another dimension, I have to take that away from the denominator. So that gets like an r to the 0. So I know it's constant outside, or it's just a property of slabs. That might just be worth remembering that field is constant above like an electrically charged plane or a slab or a current carrying slab. Then for inside, we have to reason that the magnetic field should not increase at a uniform rate because as I get farther out, I'm enclosing current at an increasing rate. Because this is essentially telling you what is happening to like the rate that you're enclosing current. Well, that rate is increasing. And there is a little theorem that you can prove that it's proportional to one more power or one greater exponent than the density function. So the linearity thing with constant density is a corollary of that. All right, wow. We were talking about that one for a while. All right, when a resistor of length and area is connected to a battery, the current through the resistor is given. Calculate resistivity. Well, of course, resistivity, we know it's going to be R equals rho L over A. Okay, but also we can just do Ohm's law. So because if we want resistivity, we need everything else, including resistance. So we also know that resistance can be written as delta V over I, because delta V equals IR. Solve that for R. Delta V was 10 volts. I was 0.004. So let's see, what do we get here? Desmos time, because I haven't done this live, apparently. 2,500 ohms is our resistance, and then we just solve. Because we'd get 2,500 is equal to resistivity times the length divided by the area. Solve that for rho. So we multiply by the area. And I got 40. 40 ohm times meters. This was really like two distinct thoughts, so I gave that a level 2. I actually don't like the star being there. I like it here. All right, this is a really tricky Faraday here. Magnetic flux through a loop is given by this function. Determine the total energy dissipated by the loop after a long time. So what is energy dissipated? So total energy dissipated is adding up all of the power contributions over time. So we got to get power. And since we know that flux change relates to EMF, the power formula that's probably the most helpful is EMF squared over R. So let's find the induced EMF. So the induced EMF is just the rate of flux change. So we just take a derivative of our flux function. And we do that, remembering to do the chain rule. So you pick up a tau on the denominator from the chain rule. Then we plug into our energy dissipation formula. So the total energy dissipated would be 1 over R is a constant, so that comes out in front eventually. And if we're integrating for a very, very long time, that means we take our upper limit to be infinity. And we're just going to square our EMF function. And let's do that. Okay. This is going to get crazy pretty fast. We square a flux phi term, we square a tau in the denominator, and multiplication happens in the numerator with the exponent. So we should get in front we get phi 0 squared. And then in the denominator, we get a tau squared and an R. And then we're just integrating from 0 to infinity, e to the negative 2t over tau. With respect to t. So then you might just want to do a little u sub here, where u is negative 2t over tau. So du would be negative 2 over tau dt. So negative tau over 2 du equals dt. So I would get negative tau over 2 times phi 0 squared times tau squared r times the integral from 0 to negative infinity of e to the u du. So I'd get negative phi 0 squared over 2 tau times r times e to the u evaluated from 0 to negative infinity. And that would be negative phi 0 squared over 2 tau times r times 0 minus 1. So I get phi 0 squared over 2 tau times r. Yeah, I'm sure that was a reasonable amount of time and not at all a 4 or 5 minute question. It is an answer choice. This gets like a 3-star only because I cannot go higher on my scale. This is an unreasonable question. There's nothing wrong with the content. It is just very time consuming. I should have just stopped at the power dissipated, don't you think? I think that would have been better. Okay, now we're back to something not crazy. A positive charge rod is placed near but does not touch an electrically neutral grounded sphere. Consider the following two scenarios. In scenario X, the rod is held near the sphere, and we cut the grounding wire before moving the rod far away. Then in scenario Y, we hold the sphere, then we move the rod, then we cut the grounding wire. So X, move the rod close, snip the wire. Scenario Y, move the rod away, snip the wire. So in scenario X, so essentially what happens is that we know that the ground is going to serve as sort of an infinite source or sink of charges. So we know that negative charges are going to enter the sphere from the ground. And it's just a matter of if we allow the sphere to keep those charges or not. So if we keep the rod close and snip the grounding wire, the negatives are trapped. But if we move the rod far away, then we snip it, the negatives were allowed to go back to the ground first. So the rod is held near the sphere, then we cut it, so it's going to be negatively charged in X, and it's neutral in Y. I forget if I called this 1 or 2. This is probably 1. Because you can see that there's a difference. All right. An electron initially has 5,000 EVs of kinetic energy, and it's moving in the plus X direction. We want the kinetic energy of the electron upon reaching X equals 4. Well, once again, we know delta K is negative delta U, which is negative Q delta V. So what is delta V? Well, we have a graph. So we know that it is a graph operation, and this would be the other one, right? We've done the field from potential, now we have potential from field. So if you integrate the potential function, that tells you the total distance down, or the E field, that tells you the total distance downhill you've gotten. So we just need to take the negative of the area. So this would just be negative of 1/2 times the base times the height, which is equal to negative 400 volts is our potential difference. So our change in kinetic energy would be negative. An electron has an elementary charge of negative 1 unit. And our potential difference was negative 400. So negative, negative, negative makes negative. So we would get a negative 400 EV change in kinetic. So this would tell us that the answer must be B, because we want the kinetic energy after reaching that point. So our kinetic energy goes from 5,000 and it goes down by 400. So delta K. So this tells us that Kf minus K0 was equal to negative 400. So Kf minus 5,000 equals negative 400. So Kf is 4600 EVs. I gave this 2-star. And I cannot stress this enough. Do not think about this as the time constraint for difficulty. Think about this in terms of the content. This is not supposed to be timed. All right, resistivity. Resistivity of a wire varies according to this function. What's the power dissipated when there's a current I in the wire? Well, anytime you have a function for resistivity, there's literally only one formula. Resistance is the integral of rho dl over A. So we integrate from 0 to L. Our function is valid for. Rho is given by this function. dl would be dx. And this is a cylindrical wire, so the area cross section is pi r squared. So we can work that out. So we'd get rho naught over pi r squared times the integral from 0 to L of 1 minus x squared over L squared dx, which would be equal to rho naught over pi r squared times x minus x cubed over L cubed from 0 to L. So 0 is 0 here, so we just get L minus, I need a 3 for my antiderivative, L minus L over 3, or L squared. I'm doing so much illegal math with this antiderivative. So we'd get L minus L over 3, which is 2/3 L. So we get 2/3 rho 0 over pi r squared times L. That's our resistance. And then power, if we have current, is I squared R. So our power is just I squared times this quantity. What is that? That's D. Yeah, there's a cluster of hard ones at the end here. A bar magnet is dropped through the center of the long solenoid shown below at T1. The bar magnet is entering the solenoid, and at T2, the bar magnet is exiting the solenoid. We want the current at each time. All right, so remember that outside a bar magnet, the North Pole is sort of a source. It's a source of field lines. So as my bar magnet first approaches the coil, there's a bunch of extra field hitting that coil that's going down. So I'm getting more B field, more B field, more B field. So if my B field is increasing this way, the induced current must create a B field the opposite way. And then if you wrap your hand around doing the right hand rule, we see that that is counterclockwise at the top. So then by symmetry, it reverses at the bottom. This is a pretty standard question. And you can see it reverses because at the bottom, you're getting sort of more of a sink there. So again, why is it counterclockwise? Well, by symmetry, we know that it's going to reverse when it exits, so it's opposite currents. But when it enters, we're getting more field, more field, more field. So Lenz's law says the induced field has to be the reverse of that, and that wraps counterclockwise. A cylindrical wire has uniform current density. Which of the following represents the magnetic field strength at distances outside of the wire? So this uses Ampere's law, right? Because we have magnetic field. So we know that the magnetic circulation is equal to mu naught times I enclosed. And since this is a cylindrical wire and we're looking outside, maybe it's important to draw a visual. We're at positions outside the wire. So we're going to do a loop. So the magnetic field B circulates over a distance 2 pi r. And then what is I enclosed? Well, current density is J. So remember that J is defined as current per area. So I is equal to current density times area. So what area do we use? Well, we know the cross section is a circle, so it's pi r squared. But also we're outside the wire. So there's not current in this region right here. So we only want the actual part of the wire. So we use J times the wire radius in pi r squared. Now, if we're inside the wire, we should take the little radius. But solving that out, we get B is equal to, the pi's go away, so it's just mu naught J A squared divided by 2, and then we get a 1 over R dependency. So you could have gotten it down to a 50-50, because if you're outside a wire, you know it falls off like 1 over R. Oh, why is it J0? Interesting. This should just say J. Lots of little mistakes today from me. It's not my best performance writing-wise, I guess. I put this as 2 because it was just really one step for this enclosed current. Now, you could have also done like a non-Ampere approach, and you could have said that B wire is just mu naught I over 2 pi r, and this enclosed current I is just J times pi a squared. That also works because of sort of the magnetic shell theorem. It does give the equivalent answer. This is the field inside. That's the field inside if you're curious. All right, two conducting loops have equal counterclockwise currents. The circular loop has radius s. The square loop has side length 2s. So this length is s, and this length is also s. Which of the following correctly compares the B field magnitudes for each shape with justification? So we actually just have to figure out if they're equal or not. So here, let's see. So for the circle, in the circle, every current element is tangent to the loop and perpendicular to the radius. Okay, that's interesting. That's a lot of words there. B circle is greater than B square because opposite sides of the square produce fields in opposite directions. Well, we can see that's false because if we go through the square, if we wrap our fingers around for each side, I get out of the page, out of the page, out of the page, out of the page. So the field is entirely additive for both the square and the circle. So that explanation is garbage for B. Then for C, the center is the same minimum distance from the wire in both loops. That's true, but that doesn't really mean anything, right? Because this distance is different, and that's still a real distance. So C's explanation is garbage. And then D, every current element in both loops contributes a field at the center in the same direction. Yeah, that's true, but I don't know how convinced I am that that's causing them to be equal. So really, it looks like, so these two explanations are just wrong, or at least they're not helpful. So we got to figure out if it's A or D. So this involves the Biot-Savart law, which says B is equal to mu naught I over 4 pi times the integral of sine theta dl over r squared. So notice that this sine theta represents the angle between the current segment and your sort of radius vector. So for the circle, just due to the definition of a circle, our current is always going to be perpendicular to the radius, right? Because the tangent and the radius are perpendicular. So this is maximized for the circle. And also for the circle, every single current element is a distance s away. Whereas for the square, there's these extra distances as well. So we see that it's actually going to be A because of the Biot-Savart law. Now there is like some extra distance on the square. Like if you get into the weeds, the field is actually a bit closer than you'd think at the center. I feel like this is like 80 or 90% of the circle field. This is hard, but the explanation A, I tried to make it pretty convincing. All right, last two. A charged capacitor and inductor are connected in series. What's the period of electrical oscillations? Well, this is LC circuit. So the only thing we know for sure for an LC circuit is that omega for an LC circuit is 1 over square root LC. So we can instantly calculate this. Anytime you're asked about time for an LC circuit, you probably want to calculate this quantity. So this gives you omega. Now what this tells you is this is the angular frequency. So unless if it says what is the angular frequency, you still have some more converting to do with your actual answer before you get the like intended quantity. So this gives me 500 radians per second. Now we have to figure out how this relates to period. So this is on the mechanics sheet. The mechanics sheet says the period is 2 pi divided by omega. So I just take 2 pi, I divide that by 500. So 2 pi over 500. I get 0.0126 seconds. And if we round that, that rounds to 1.3. 2 star because you had to convert, you had to do the period sort of swap here. Similar if you wanted frequency instead of angular frequency, you'd have to do a divide by 2 pi. All right, last one. Gaussian sphere is placed near a bar magnet. Which of the following accurately describes the net magnetic flux of the Gaussian sphere with correct justification? Well, as soon as I see this is a 3D surface, I'm done. Because as soon as you see 3D surface, we know that the magnetic flux equals 0 through any 3D shape. That's all I need to say. Doesn't matter what's going on with the bar magnet. Bar magnet can be outside, it can be inside, because magnetic field lines always loop on themselves. Well, that's an awful magnetic field line. Magnetic field lines always form closed loops. So because of that, any surface where there's an in and an out, all the field lines that go in also go out. Doesn't matter anything here. So I just see the magnetic flux is 0 because the magnetic flux through any closed surface is 0. Now, if this was like an electric charge problem, this would be the answer. If it was like Gauss's law for electric fields with point charges, where flux depends on Q enclosed, flux does not depend on Q enclosed for magnetism because there is no magnetic charge. Magnets always come in poles. All right, I think that certainly lived up to my claim that this is a very difficult free response. Man, this is a very difficult multiple choice set. So again, do not think about this as being like a timed thing. Think about these questions as sort of their content. This really does cover like practically everything in E&M. And I'm sure anything I missed would be in like my first multiple choice set. So hopefully this gave you a good overview of like the breadth of things we can ask with this.